Data has three main uses: to describe what has happened, infer cause and effect, and to make predictions. They are also known as data analytics, causal inference, and machine learning. Let's take a closer look at each one, starting with data analytics. Let's say you own a shop and have sales data. Raw data isn't useful. You need to generate useful insights. Start by calculating things like totals and averages. Here, Thursday looks like the busiest day of the week. Why not check if there's enough employees on Thursdays? But before making big decisions, look for evidence that this confirms your beliefs. For example, sort daily sales in descending order to look for outliers. Are high average sales on Thursday due to one Thursday? To reduce the effect of outliers, use the median, the number in the middle of a sorted list. When you present data, ask yourself, what message do I want to send? Then work backwards. If you need to convince HR to let you hire more employees, have a graph like this. A big title with what you want, and a graph that shows what happened when employees left. If you need to show that most of your customers are millennials, one big number may be all you need. Plotting data over time helps us identify trends. Finding correlations can help us identify patterns and areas for growth. But correlation is not causation. The gold standard for showing cause and effect is an experiment. Here's a simple example of an experiment. Suppose you wanted to test the effect of giving weight loss pills on weight. You'd get a bunch of participants and split them into two groups. You'd then give weight loss pills to only one group. After a few weeks, you calculate the average weight of participants in both groups. In this case, the average difference is 3 kilograms. But could this difference be due to chance? To answer this question, you need to calculate the p-value. The p-value tells you how likely simple chance only can result in a weight difference of at least 3 kilograms. If the p-value is below a threshold, usually 0.05, it's unlikely that chance can explain this difference. Let's say the p-value is 0.01. Then you can conclude that weight loss pills affect weight. What if you can't conduct an experiment? A few years ago, Uber wanted to know how much demand would decrease if it raised prices. But it's dangerous to experiment with raising prices for randomly selected customers. So it looked at what happened when the search pricing multiplier changed. At Uber, the multiplier is determined by a formula known as a search generator. The search generator calculates how high demand is relative to supply and spits out a number. The number is then rounded to one decimal place to become the search pricing multiplier. When the search generator outputs 1.249, it gets rounded to 1.2. But if the search generator outputs 1.25, it gets rounded to 1.3. Both conditions are practically identical. However, prices in one condition are nearly 10% higher than in the other. So we can see what happens to the purchase rate when a search generator goes below 1.25. And we can also see what happens when a search generator goes above 1.25. The gap between both lines gives us an idea of how price increases will affect Uber. And we can look at other discontinuities as well. More detailed analysis found that price increases of 1% would lead to a 0.6% demand decrease. In other words, increasing prices could increase revenue. This technique of looking at discontinuities is called regression discontinuity design, or RDD. Another way to determine cause and effect is difference in differences. Let's look at an example. Do minimum wage hikes affect employment? In 1992, New Jersey increased its minimum wage by almost 20%, but neighboring Pennsylvania did not. Thus, only New Jersey's fast food restaurants increased their hourly wages. Two economists studied the fast food industry in New Jersey and eastern Pennsylvania. They looked at employment both before and after the wage hike. The authors found that New Jersey's fast food employment increased after the wage hike, but fast food employment in Pennsylvania decreased. Thus, New Jersey's fast food employment increased relative to Pennsylvania. Moreover, the results couldn't be explained by any other change the authors observed. The authors concluded that increasing the minimum wage may not decrease employment. This study was controversial in many ways. First, the results contradicted economic theory. Second, it only used data from 1992. The study could have been much more convincing had it started earlier and ended later. But this study illustrates the key idea behind difference in differences. Find two groups that are as similar as possible, except that one group was affected by a change. Compare how outcomes evolve in both groups. Let's move on to the third use of data, making predictive models. Let's say we want to predict house prices. To keep things simple, let's assume we have data on 500 houses. We know their price, their size, and their age. One way to predict house prices is to build a linear model. For example, an equation that predicts a house's price like this. Multiply the house size by 1000, then multiply its age by 10,000, and subtract the second number from the first. So a house that's 2,000 square feet and 50 years old has a predicted price of $1.5 million. As a house's age increases, the predicted house price decreases in a straight line. When house size increases, predictions increase linearly. That's why this model is called a linear model. How are these numbers determined? You'd start off with an initial guess, usually 0. Next, make predictions based on these initial guesses. Right now, all your predictions are 0. Then calculate your loss, which is a fancy way for saying how far your predictions are off. What's your loss now? Well, let's just say it's some very big number. But you can try out different guesses and see if your loss decreases. The linear model has a certain magic to it. There's a formula to help you decide your next guess. Keep using the formula again and again, and you'll find that your loss will stop decreasing. You can then use the last set of numbers you tried to predict house prices. A linear model is simple. It can also work well in many situations. However, you can often get better results from a neural network. What's an example of a neural network? Let's say you're Google News. You need to automatically classify news articles into one of 4 categories: US, World, Business, and Technology. If you were classifying each article manually, you'd combine the words into phrases. For example, Toyota Motor Corp has 3 words. Phrases combine to become concepts. Concepts combine to become topics. An article's topics determine its category. So business is a reasonable category for this article. And that's also the essence of how neural networks work. A neural network has many layers of nodes. Each node is called a neuron. The lower layers detect words and phrases. The upper layers detect concepts, topics, and categories. The neural network itself doesn't name topics or concepts, but they're often intuitively recognizable to humans. Let's zoom into one piece of the puzzle. There's a news article talk about Japanese car makers. Let's assume the English language only has 3 phrases. You might give 1 point if the article mentions Toyota or Honda, and give 0 points or even negative points if the article mentions cat food. Then articles on Japanese car makers should have higher scores than articles that aren't. And the layered structure helps start a chain reaction. High scores on a Japanese car node result in higher scores on a car market competition node, and so on. But exactly how many points should one give? Like in linear regression, you start with initial guesses. Keep modifying your guesses. Stop when you can't increase your prediction accuracy. In practice, each layer has many more nodes. One special node is the bias node. It automatically adds x points when turned to x. For example, if the node has a value of 1, then 1 point is automatically added. When the bias node is combined with a simple trick, the neural network can detect incredibly complex patterns. The trick is called ReLU. It records the score as 0 if the actual score goes below 0. Let's see how this works. Imagine we are determining if an article describes US-Japan car industry competition. We can use 3 neurons to find out: the bias neuron, US car makers, and Japanese car makers. The bias node has a value of -3, and the other 2 nodes have a value of 2 each. What happens when both US and Japanese car makers are mentioned? The US car makers and Japanese car makers will transmit 2 each to the top neuron. The top neuron will have a recorded score of 1 and can be viewed as activated. What if only US car makers or only Japanese car makers are mentioned? The top neuron will have a recorded score of 0 and can be viewed as not activated. We can detect this pattern with just one layer of 3 neurons. With many layers, the network can discern incredibly complex patterns. And that's some of the most important ideas in 3 big branches of data science. Data analytics helps us identify key patterns and trends. Causal inference helps us determine cause and effect. Machine learning helps us make predictions. Most data scientists will specialize in one branch, but it always helps to know all 3 branches. I hope you enjoyed the video.